Resistance. Resistance is the property of a material that opposes the flow of electrons. Let me explain this. Imagine you are trying to move through this crowded place. This crowded place can be a busy market or a school hallway full of people. I'm repeating. You are trying to move through this crowded place. This crowded place can be a busy market, a school hallway full of people. More the people there are, harder it is for you to move quickly because you keep bumping into the others or getting blocked, or you keep colliding with others or getting blocked. A similar phenomenon happens in the wire when this electron moves through this wire. It collides with the atoms of the wire, with these atoms of the wire. First, it will collide with this atom, then this. It will collide to these atoms and it will feel opposition. This opposition to the flow of this electron is known as resistance. Hope you got the point. I'm repeating, you are trying to move through this crowded place. You will feel opposition because you will collide with the people. Same when this electron moves through this wire, it collides with these atoms, and this opposition to the flow of this electron is known as resistance. Resistance is a material property. It's a copper wire, here a piece of silver wire. Silver wire has more resistance because it is more crowded as compared to this copper wire. Copper wire has less resistance as compared to silver. So resistance is a material property. Resistance is a property of a material that opposes the flow of electrons. This electron collides, this electron feels opposition because of the collision. That opposes the flow of electron is known as resistance. Now, according to Ohm's law, V is equal to IR. By rearranging, we get R is equal to V over I. This R represents the resistance. So, another definition of resistance is the ratio of voltage and current. Resistance is the ratio of voltage and current 2 divided by 3. We can say that 2 ratio 3. Same. It's a ratio of voltage and current. Now the SI unit of resistance is ohm. It's a symbol of ohm. Now resistance is measured in ohm, voltage in volts, and current in amperes. So ohm is equal to volts per ampere. Ohm is equal to volts per ampere. Now here the definition of ohm. For example, if 1 volt potential difference is applied, 1 volt potential difference is applied, and 1 ampere current flows through the conductor, then the resistance will be 1 ohm. 1 volt potential difference is applied, 1 ampere current flows, then the resistance will be 1 ohm. Same. If 1 ampere current flows, when 1 volt potential difference is applied, then the resistance will be 1 ohm. It's the definition of ohm. Now, factors affecting the resistance. Factors affecting the resistance can be classified as physical factors and non-physical factors. Factors affecting the resistance are classified as or can be classified as physical factors and non-physical factors. Physical factors include length and the thickness of the wire. Now length. Longer wires have higher resistance. Let me explain this. This is a longer wire as compared to this one. So in this shorter wire, this electron will collide first with this electron, then this here, and it will move through the other end of the wire. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, almost 10 collisions. In this shorter wire, this electron will collide with these 10 electrons. But in this longer wire, this electron has to collide with more than 20 atoms. More than 20 atoms. So, more collision, more resistance. Collision is directly proportional to the resistance, and collision is directly proportional to the length. In longer wire, more collisions. Collision is directly proportional to the length. Longer wire, more collisions. More collisions, more resistance. So, resistance is directly proportional to the length. Longer wire, more collisions, more resistance. So, longer wire has more resistance. Now, thickness. Take it like a wider road and a narrow road. In wider road has less resistance or traffic jam, less traffic jam. In narrow roads, more resistance or more traffic jam. So, it's a thicker wire. Thicker wire is like a wider road. So thicker wire has less resistance, like a wider road has less resistance or less traffic jam. So resistance is inversely proportional to the cross-sectional area. What is the cross-sectional area? Let me explain this. This rod. This area of the rod is known as cross-sectional area. So this thicker rod has larger cross-sectional area and this thinner rod has smaller cross-sectional area. It's the cross-sectional area of this thinner rod and it's the cross-sectional area of this thicker rod. So, wider rod or a thicker wire has larger cross-sectional area. Larger cross-sectional area, less the resistance. So cross-sectional area has inverse relation with the resistance and length has direct relation with the resistance. So by combining these two, we get R is directly proportional to length over cross-sectional area. Here, when this proportionality is converted into equality, a constant rho comes here. This rho is the resistivity of the material. Now, what is the resistivity? Resistivity is the resistance of a material with a length of 1 meter and the cross-sectional area of 1 meter square. For example, I have a rod or a wire. Take it like a wire, as a wire. For example, the length of this wire is 1 meter and this cross-sectional area is 1 meter square. It's not a 1 meter square, but consider it as a 1 meter square. If the length is 1 meter and this cross-sectional area is 1 meter square, then the resistance of this wire or material will be is known as resistivity. Resistivity is the resistance of material with a length of 1 meter, and the cross-sectional area of 1 meter square. Then the resistance will be or a resistance is known as resistivity. Resistivity doesn't depend on the size or shape. Resistivity allows us to compare different material, copper, silver, aluminum. Resistivity is for comparison between different materials. The SI unit of resistivity. The SI unit of resistivity is ohm meter. For example, by rearranging this equation, we get rho is equal to R A divided by L. By rearranging, A will be multiplied with this R and L will be divided under this RA. So the SI unit or resistance is measured in ohm, area in meter square, and length in meter. This meter and this meter square, after the simplification, we get ohm meter. So the unit of resistivity is ohm meter. This meter and this square will cancel out each other. So ohm and 1 meter is left. The unit of resistivity is ohm meter. The unit of resistivity is ohm meter. Now, non-physical factors. Non-physical factors include temperature and the material of which wire is made of. I'm repeating, non-physical factors include temperature and the material of which wire is made of. For example, this wire is made of silver particles and this wire is made of copper particle. So, non-physical factors include material and temperature. Resistance and resistivity change as the temperature changes. Think of it like a boiling water. When we say the water is boiling, but actually heat increases the temperature and the kinetic energy of the water molecules. I'm repeating, when we say the water is boiling, but actually heat increases the temperature and the kinetic energy of the water molecules. As you can see that the kinetic energy of the water molecules has increased. Same phenomena happens in this wire. As temperature rises because of this burning candle, I'm repeating, as temperature rises because of this burning candle, the vibrational kinetic energy of the atoms increases. Same like water molecules, the kinetic energy of water molecules. Same phenomena happens. The vibrational kinetic energy of the atoms increases because of heat or rise in temperature. So, as a result, this electron first collide with this atom because of its vibrational kinetic energy. Then it will collide with this atom. So this increase in temperature will lead more collisions between electron and the atoms. I'm repeating, this rise in temperature due to this burning candle will lead more collisions between electron and the atoms of the wire. So more collision, more the resistance. Collision is directly proportional to the resistance. So as a result, rise in temperature leads to rising or increasing resistance for conductors. So as temperature increases, the resistance of the conductor also increases. This equation describes the phenomena of change in temperature as a function of change in resistance, or not the resistance at 0 degree centigrade, or T resistance at higher temperature means at 20 degree, or T resistance at 20 degree or not reference temperature, 0 degree or not. And alpha, alpha is the temperature coefficient. This shows how resistance behave with temperature. And RT is 20 and T is 20 and T naught is 0 degree. For conductors, this temperature coefficient of resistance alpha is positive. This alpha, temperature coefficient of resistance, this alpha is positive for the materials whose resistance increases with increase in temperature, and negative for the materials whose resistance decreases with increase in temperature. For example, for conductors, alpha is positive. As we know that the resistance increases with increase in temperature for the conductors. But for semiconductors, alpha is negative because the resistance of semiconductor decreases with increase in temperature. For example, by increasing the temperature due to this burning candle. In semiconductor, initially there is, or for example, two electrons. There are two electrons initially, but when temperature rises, more electrons from the valence shell gets enough energy and jumps from valence band to the conduction band because of the rise in temperature due to this burning candle. These electron jumps from valence band to the conduction bands, and the number of free electrons are increasing with the increase in temperature. More the free electrons, more the current. More the current means less the resistance. So with rise in temperature, current is increased, means the resistance is decreased. That's why alpha is negative, because the resistance decreases with increase in temperature for the semiconductor materials. And for conductors, we already discussed in detail. In semiconductor, the number of free electrons remains constant. They are already higher in numbers. As temperature increases, for conductor, their vibrational kinetic energy increases, but the number of electron doesn't increase, they remains constant. But in semiconductor, the number of free electron increases, that's why the current increases and resistance. The current is increased, means the resistance is decreased. Now for electrolyte. For electrolytes, alpha is also negative. For semiconductor, alpha is negative. For electrolyte, alpha is negative. Why? In electrolyte, the current is because of the movement of ions. For example, in this electrolyte, there is positive and negative ions. And the current flows because of these positive and negative ions. As temperature rises, because of this burning candle, as temperature rises, the viscosity means thickness. The viscosity or thickness of this liquid decreases, which allows the ions to move faster. They move because the viscosity is decreased and they get thermal energy from this heating source. So viscosity is decreased, which allows the ions to move faster. These faster moving ions increases the current. The current is increased, means the resistance is decreased. That's why electrolyte alpha is negative for electrolyte, because resistance decreases with increase in temperature for electrolytes. Same phenomena happens for ionized gases. The current can flow through the gases. The The lightning in thunderstorm is an example. The current or electricity flows from the clouds to the ground through the ionized gas. It's an example for the flow of electricity through ionized gas. So alpha is negative for ionized gas. As temperature rises, ions, the number of ions and free electron increases. That's why their conductivity increases with increase in temperature. Conductivity increase means the resistance is decreasing. For alloy is the mixture of different conductors, so they behave same as conductors. So alpha is positive for inductors, for alloys alpha is also positive. Their resistance increases slightly with temperature. For superconductor, at low temperature, the resistance of superconductors becomes zero. So alpha is irrelevant at low temperature for the superconductors because there is no resistance for superconductors. Now, proofs. Prove that by doubling the length, the resistance becomes doubled. Prove that by doubling the length, the resistance will be doubled. By doubling length means L prime is equal to 2L. The resistance will be doubled for constant cross section area. Cross section area is constant, but the length L prime is equal to 2L. It's a question. Now we have to find the resistance. We know that R is equal to rho L over A, and then R prime will be rho L prime over A. A is constant for both. For constant cross section area, by doubling the length, the resistance will be doubled. We have to prove. By putting the value of L prime is equal to 2L. By putting the value of this, L prime. By replacing L prime with 2L. Now, by rearranging, rho L over A is equal to R. So, replace rho L over A with R, hence proved. R prime is equal to 2R. This shows that resistance will be doubled by doubling the length. Now, another proof. Prove that by doubling the area, the resistance will be halved for constant length. It's a question. By doubling the length, by doubling the cross section area, the resistance will be halved for constant length. So again, R is equal to rho L over A and R prime is equal to rho L over A prime. So here L is constant, here A was constant. So by replacing A prime with 2A, it's given in question. And then by rearranging rho L over A is equal to R. So by putting the value of rho L over A, R prime is equal to 1 over half of the R. So the resistance will be halved. That's all.